Thank you very much. So I'm going to tell you about the James Webb Space Telescope, which is the successor to the Hubble Space Telescope. Now, when astronomers first started thinking about what comes after Hubble, they thought a lot about this picture, or pictures like this. This is the Hubble Ultra Deep Field. It's the faintest picture that humanity had ever taken up until July of this year. Now, in this picture, it's filled with galaxies. Almost everything you see are galaxies outside our own Milky Way. There's only maybe one or two stars that are kind of in the way. And when you look at a picture like this, you see the bigger and brighter galaxies that have structure. But what really excites the astronomers are the galaxies that are the furthest away in this picture. And that is because as we are looking at these galaxies, the light from those galaxies has traveled most of the age of the universe to get to us. And so we're looking backwards in time. Telescopes are time machines. We can look backwards in time to when the universe was younger just by looking at things that are further and further away. So these three examples, I realize they're just kind of small, faint red smudges of galaxies, but the light was emitted within the first billion years after the Big Bang, and the Big Bang was 13.8 billion years ago. So we're looking at light that has traveled almost 13 billion years to get to our telescope, in this case Hubble. But one thing that was really interesting when we look at these and study them in more detail is that some of these galaxies are already several 100 million years old. So think about that. Within the first billion years after the Big Bang, we're seeing galaxies that are already several 100 million years old. And what astronomers and physicists want to do is look at the beginnings. How did things start? We want to find the first galaxies that formed after the Big Bang in a field like this. And to do that, we have to go beyond Hubble. So there's three ways in which James Webb is different from Hubble. First of all, it is a bigger telescope, 6.5 meters primary mirror diameter versus 2.4 meters for Hubble. And this allows us to collect more light to see things that are fainter and then on average see things that are further away. But another thing that we have to do is that Webb is an infrared optimized telescope. And the reason for that is that as the light is traveling for 13 billion years through an expanding universe, the light itself is expanded. So light that is emitted at short wavelengths in the ultraviolet or visible light is pushed out beyond where we can see into the infrared. And infrared is heat. And Hubble is a room temperature telescope for a couple of reasons. One is that it's in low Earth orbit and it goes in and out of sunlight every 90 minutes. And so to keep a constant temperature, we have to heat it to keep it at room temperature. But also we sent astronauts up to Hubble and we didn't want them freezing to the side of a cryogenic telescope. Webb, however, is cooled in order to be sensitive in the infrared. It's cooled to a temperature of 218 degrees below 0 Celsius. This is just 55 degrees above absolute zero, and some parts of Webb are much colder than that. And then finally, the other big difference between Hubble and Webb is that Hubble is in low Earth orbit, 600 kilometers above the Earth, goes around the Earth every 90 days, and we put Webb 1 million miles away at a special orbit called the second Lagrange point, and L2 goes around the Earth once per year as the Earth goes around the Sun once per year, and the Sun, the Earth, and the telescope are always lined up. And this allows us to put Webb behind a tennis court-sized sun shield that allows the telescope to radiate all of its heat out into empty space and cool to these very, very cold temperatures. Now, I'm going to show you the coolest selfie I will ever take in my life. There was a time when the Webb mirror was pointed at the viewing window inside the clean room. Now, they don't let scientists go in the clean room. That's for the highly skilled technicians and engineers that are actually working on the hardware. But they had it pointed at the window once, and so I went over and got this picture. This is the only picture I'll show you before the launch, because now we have the launch, Christmas Day of last year. There should be sound. Okay. So anyway, the Webb is an international partnership between NASA, the European and Canadian space agencies, and one of the things that the Europeans gave us was the launch vehicle, the rocket. And the cool thing, if you'd had sound, is that to launch a French rocket, they count backwards in French. After 6 months of commissioning the telescope, turning everything on, getting it to work, we brought out our first images, and NASA was scooped one day by this guy, who decided that he wanted to be the person to bring out the first Webb image. And that was great for the project because, just to put it in perspective, the last time a US president had made an announcement of a NASA science result was Bill Clinton in the 1990s with one of the Mars results. So this was cool to have President Biden bring out our first image. And when we brought out our first pictures taken with Webb, first scientific pictures taken with Webb, they followed along the science themes that we, the astronomers, had written down almost 20 years ago about what science Webb should do. The science goals were, starting with the Big Bang, find the first galaxies that formed in the after the Big Bang, trace the evolution of galaxies over time to form galaxies like our own Milky Way that we live in, study the formation of stars and their planetary systems in those galaxies and in our own Milky Way, and finally, study of planets, including both planets around other stars that we call exoplanets and planets in our own solar system, and look for the conditions for life on other planets. And so the Webb science is already addressing these 4 themes, and I'll take you through them a bit. This now is the deepest picture that humanity has ever taken in the infrared, and it shows a cluster of galaxies that is full of dark matter with gravitational, where the gravity is lensing the light from the background galaxies and stretching some of them out and also magnifying some of these background galaxies, which gives our telescope an extra boost to see extra far in this field. And we also have several other fields, what we call deep fields, where we're looking at galaxies and the statistics of the galaxies that we find. This is the Cosmic Evolution Early Release Science Program, and it's not quite as deep as the one I just showed you, but it also covers a bigger area so that we can find rarer objects. And I've pulled out a few of the brighter, more nearby galaxies down at the bottom, and in number 4, we actually discovered a new supernova going off while we were observing this. But again, the scientists are, like myself, are most excited by the most distant things in this picture. And so here we have pulled out a candidate for a galaxy where the light has been traveling for 13.5 billion years of the 13.8 billion years since the Big Bang. That means that this galaxy emitted its light just 300 million years after the Big Bang, which is where the theorists tell us could be the first galaxies turning on. Now, I have to say this is a candidate. We need more data. We need to follow up with a process called spectroscopy, where we spread out the light and look at the constituents of this galaxy and see whether it's made from the pristine material, hydrogen and helium, that came from the Big Bang, or whether it has some heavier elements that have been processed through an earlier generation of stars. Those data are being taken in December, and I can't wait. But then galaxies change over time, and one important way that they change is by colliding. Now, when galaxies collide with each other, they don't go bang, they kind of go slosh, because most of a galaxy is empty space in between the stars, and the stars themselves very rarely actually collide. But what does collide is the gas in between the stars, what we call the interstellar medium. The gas between the stars will collide when galaxies collide, and you see here that Webb is very good at picking out newly formed stars, and there's a band of red in between two of these galaxies that show where the collision of these two galaxies has triggered star formation. Now this is a picture of a star-forming cloud within our own Milky Way in the Carina Nebula. And in this picture, there are lots of newly forming stars that appear as yellow in this picture. Now, star formation is a very messy process. Newly formed stars the gas and dust will collapse into the star and form the planets around the star, but some of it gets ejected. And we have here, focusing on in the lower right, we have a newly formed star system, and then up at the top of the picture, we can see a cloud of gas that has been ejected from this system and traveled across the picture because as the star was being formed. This is an iconic picture taken by Hubble. It's the Eagle Nebula, sometimes called the Pillars of Creation. And this, again, is a region where stars are forming. And the stars form in the most dense part of the dust clouds. And in the visible light, we can't see in, but infrared allows us to see through some of this dust. The Webb image allows us to see through the dust into the action where the stars and their planets are actually forming. And you can see this at the end of the pillars. There are little red spots, and those are the newly forming stars in the densest parts. Now, as I said, we also want to study planets around other stars, what we call exoplanets. And a very powerful technique that we have is when the planet crosses in front of the face of its star, and light from the star actually will go through the atmosphere of the planet on its way to our telescope. And we can analyze that light to see the constituents. What are the atmospheres made of? Now, the movie is not actually an exoplanet. It's a transit of the moon across the face of the sun. And if this had been taken from the Earth, we would call that a solar eclipse, and the size of the moon would look about the same as the size of the sun. This video was taken by one of our solar observing satellites, and it was not taken from Earth, so the relative sizes are not the way you see them from the Earth. But this was the first detection of carbon dioxide on an extrasolar planet, an exoplanet, made with Webb just recently. Now, within our own solar system, we have this beautiful picture of Jupiter. It shows the rings of Jupiter, and you might have thought that only Saturn has rings, but Saturn's got a big ring, but most of the outer solar system planets do have their own rings. And we detected a couple of the smaller moons of Jupiter and the northern and southern aurora in the atmosphere of Jupiter. This is a beautiful picture of Neptune, and we can again see the rings of Neptune and some of the cloud features on the surface. I'm going to say that Webb is also a good citizen. We work with our fellow NASA missions, and NASA recently impacted a spacecraft into an asteroid in order to test whether we can change the orbit of an asteroid. So on the left is the last full picture that the DART mission took of that asteroid. In the center is the Hubble Space Telescope data of the impact, and on the right is the Webb data. And this was also the first time that we had Hubble and Webb working together, pointed at the same object at the same time. And I should say Webb is a successor to Hubble. It's not a replacement. We love to have them both working together because they do have different capabilities. We had a big impact on the public. Front page of the New York Times and Washington Post 2 days running. Our images were in Times Square in New York, Piccadilly in London. A couple of bands picked us up, Coldplay, and Very important to our project manager, who is a huge parrot head. He loved seeing Jimmy Buffett use our images in a concert in Maryland. We made the Google Doodle, and if you go to the post office, you can buy the Webb Space Telescope stamp. So I'm going to leave you with, there's a whole lot more to come. We, of course, have a website. We have a blog where we bring out some of the things that aren't quite as big enough for press releases. We have an image archive, and of course, Twitter, Facebook, YouTube, Flickr, Instagram, etc. Thank you very much for listening.
So John, before we let you go, you have been at NASA for 3 decades.
Almost.
This project has taken an enormous amount of time. What's it like to plan something that spans multiple decades while also knowing that at any point something could go catastrophically wrong and all that effort could be wasted?
Okay. Yeah, so I started working kind of seriously on Webb in around 1998. And 1998 was when my son David was born. I was working on those 4 science goals, writing down the plan for Webb in 2004 when my youngest child Avery was born. So I have 3 children and 1 space telescope. And we delivered the space telescope last Christmas Day to orbit 1 million miles away. And of course, we're in constant communication over radio with the telescope. And my wife and I delivered Avery, our youngest, to college 4,000 miles away. They're going to the University of Edinburgh in Scotland just last month. And of course, we're in constant communication. But in both cases, you do your best to give them what they need to succeed. And you send them off, and you hope you did a good job. And I have to say, the Space Telescope is doing wonderful work, and my 3 kids are also doing wonderful things with their lives. Thank you very much.